Hi, I'm Ade. I'm a technical solutions engineer at Google, and I'm basically hosting this talk by the wonderful people at L-Shift and Cohesive FT about RabbitMQ. I've known 2 or 3 of these people for a few years now, actually, and I thought invite them along. They can talk about their stuff, and we can see how cool it is. Without further ado.
So my name is Alexis Richardson. Thank you for coming today. I work for a company called Cohesive FT, and together with L-Shift, we've created RabbitMQ, an open source messaging broker, which I want to tell you about today. The structure of the talk will be in 3 parts. First, I will talk about the business background to AMQP, which is a new open standard for business messaging. It's an internet standard, like HTTP or XMPP. Then Matthias, who's the head of engineering on the project, will talk about the architecture of RabbitMQ, the product, and explain why we chose Erlang OTP as the platform to build it on. And then at the end, Tony Garnett-Jones will talk about some research that we're working on, new stuff to do with web messaging in general, and future directions for AMQP, possibly XMPP, and other internet standards. And then we can have some questions. Okay, so the first point is that RabbitMQ is nothing more than a messaging broker. That's all it does. It takes messages and it sends them on to other places. And it does that in a pretty smart way. AMQP is the protocol that it implements. There are lots of plugins for other protocols like XMPP, HTTP, and STOMP. And it's completely language neutral. So you can write to it or read from it from any language, just like if you're using TCP or HTTP. And I wanted to introduce messaging. Some of you may not have used messaging very much. Messaging is a way of dealing with sending data over the internet. People use it to scale applications. There are some applications that are famous for having run into some scalability issues recently. Here's one of them. Obviously, the markets have been in the news recently. Another reason for using messaging is market data, which is a form of monitoring. You might use messaging if you want to send lots of data to lots of people at the same time. Or if you need something delivered and you don't know who it's going to be delivered to. So this is a generalization of the notion in SMTP of sending a message to another party. So it has notions of addressing in it as well. Or you might need things done in a certain order. Another reason that people use messaging is it provides seriality guarantees. So you can use it in transaction systems for guaranteeing order. Especially in distributed systems, that can be very important. And lately, people have been talking about the cloud as a way of dealing with distributed applications that aren't run by you but are managed elsewhere or distributed or federated in some way. And messaging is very important as a fundamental infrastructure for cloud applications because you need to monitor them, you need to send data between them, you need to upload applications into the cloud and get them back from the cloud. And sometimes you need to do that reliably or transactionally or with the properties of delivery that we'll talk about. Okay, another point about messaging is it's really everywhere. It doesn't have to be used in any one way. Here are some topologies that you've probably seen before, which are used in messaging scenarios. Peer-to-peer is a very common mode where you've got lots of parties who are of equal business status talking to each other in some virtual network. Another one is client-server. This is very commonly used for patterns like what's called store and forward, where you have to deliver something to one other party in a network and some major party or hub will take responsibility for that. Another pattern is for service architectures, what's called a service bus. This is when you virtualize request response over an asynchronous backbone. And here are some use cases for messaging. Later on, people might want to check this link. This is a really nice 10-slide introduction to why you might need messaging, fleshing out some of the things I've been saying by Bob Pasker, who founded WebLogic back in the 90s. But here are the main things. I've summarized them already. Queuing and buffering is very important. Monitoring is a very common use case, and load balancing and scalability. So what are the ways that people already use messaging? Well, the thing about messaging that's interesting from our point of view is up until now, it's either been done in ad hoc ways, or it's been done using what's called messaging middleware, which is third-party software which you buy as a product either on license or you get as open source. And then it implements a proprietary API or an API that offers a degree of portability, but not the level of interoperability that TCP or HTTP do. And our claim is that this lock-in effect has reduced the uptake of messaging across the world. And here's why. Typically, the more that you have proprietary APIs, the more work needs to be done to actually integrate the product into the surrounding environment. And the more maintenance work has to be done in order to keep it going over time. And if there's a single company involved in this, then that can put great risk on the end user, who then develops a dependency on the company which may not exist in a few years' time. And quite often, people have been really hampered by this. In fact, AMQP got started because a bank, JP Morgan Chase, realized that they were losing money by locking themselves in this way to multiple different vendors, and thought, well, wouldn't it be easier if messaging was just plug and play like TCP and HTTP? And you can see this if you look at the messaging market. The messaging market for software products, middleware products, is IBM, Sonic, Tibco, and a few others. And it's about $1 billion, which is kind of trivial compared to companies like Google, Yahoo, Amazon, etc., and other software companies that provide third-party software. It's not a very big market because the complexity of dealing with middleware has kept the use cases fairly narrow. And there's lots of other use cases that just aren't being addressed. And this we believe, is because of the lack of open standards. So the open standards that we admire and that JP Morgan looked at when they decided to start up AMQP were things like TCP and SMTP. SMTP is clunky, but it does actually work. People are able to send emails, and the failure modes are ones that human beings can deal with reasonably well. One of the problems with SMTP is spam, so that was something that might be addressed in a future improved version of messaging. HTTP, I don't think I need to talk about the success of that. And TCP, well, the interesting thing about TCP is for a while there were different competing network protocols in the 80s. But once the things settled down, people really did achieve interoperability and could actually build new applications that were relevant to their business on top of them. So that was the hope with AMQP as well. And again, because they're not being provided by a single software company, there is the opportunity for you to build systems that outlast any particular supplier and have a marketplace that lasts a long time. And for people to think up new ways of using the technology that aren't dependent on asking the original engineers who wrote it how to do that. So you can sort of see this if you imagine what would happen if we never had TCP and instead had to use a single product from a single vendor, say IBM or Novell, or HTTP. If we could only use a single vendor's web services, that would make things difficult. And at the moment, you can see some transition points. XMPP is a new standard. It's only been around for about 6 or 7 years. And people are still using AOL. People are still using MSN. People are still using Yahoo Instant Messaging. Google obviously have Gtalk, which is based on XMPP, I believe. But if you look at the numbers, XMPP has only taken 10% market share across the world, approximately, on average, I think. And AMQP is even newer. So, we hope to achieve this benefit with these standards. And if you care about this kind of thing, this is a sort of very simplistic way of looking at application layer protocols. Sometimes L4, sometimes L7, depending on which stack you're talking about. Essentially, we're talking about something that is as asynchronous as SMTP. So we're talking about messaging, but it's business messaging. It's got a degree of reliability, either stability under load or the failure modes are exposed in the protocol so that you don't have to deal with errors by hand as you do with SMTP. Or you've got transactionality properties like rollback, for example, which you don't have with other protocols. Now, the point about this picture is also that there are several candidates to fill in this question mark. And at the end of this talk, Tony will talk more about research that we're doing in areas around this that don't just involve AMQP, but other ways of doing reliable messaging with HTTP and XMPP. But the point is there is a gap. And AMQP is aiming to fill that gap with these fundamental properties: routing, delivery, and fidelity. So routing is, where do I send messages? Who do I send them to? Delivery is a queuing property. How do they get there? How do they get buffered? Do they get sent to multiple consumers at once? Or do they get held in place for one specific permitted consumer to take exclusively? And then how do you build more complex patterns out of that? And fidelity is what we think of what goes in must come out property. which is originally delivered by MQ series, which allows you to know transactionally that a party has received the message that you've sent and send messages exactly once. So it's an idempotency property on delivery. And this is the model in a nutshell. Again, I recommend that you go to our website and look at the specs for more details. The point about AMQP is there's three tiers. Producers and consumers are clients of the system. There is a logical tier of what are called exchanges, which are routing tables, which deliver the routing property. There is a set of queues which buffer messages on behalf of consumers and introduce quality of service properties like persistence and transactionality. And collectively, there's a set of properties which deliver fidelity across the whole system. But if you assemble an AMQP broker, you just give it simple instructions as to what exchange to send messages to, which queues should be, in the terminology of AMQP, bound to exchanges, and so which messages they receive based on routing keys. Routing keys are like email addresses or newsgroup names. So you can send things like to Matthias@lshift.net. Or there are pattern-based routing keys as well. So I can say ibm.buy.100 and match on the word buy in the middle of that group. And that gives you the publish, subscribe, and messaging properties that you see in the middleware products, but in a standardized way. And you assemble these into clouds of brokers, which allow producers and consumers essentially to communicate in a peer-to-peer style. This is business peering rather than P2P in the technology sense. And here's a quick picture of the underlying technology. The point here is that we're using TCP for the connection at the moment, although in the future other connections, other network transports will be allowed. And channels represent modes of communication for messages between producers and consumers, exchanges and queues, multiplexed over this connection. And Matthias will talk more about that a bit later. Where does AMQP come from? Well, there's a working group, which is the standards body. What's interesting about this is there are actually end users in it who are guiding the outcome, which is unusual. Many standards are only produced by vendors, which, like the web services standards, which possibly has held them back or made them a little bit too complicated. Rabbit website, I recommend that you look at this and some things that people say about it. Generally, people are happy with Rabbit. They find it very easy and quick to set up a cluster of brokers, and things tend to work really well the first time. Lots and lots and lots of clients in different languages. Again, go to the website or some of the links that we'll give you later to check those out. It's pretty fast. We did some testing with Intel. We're able to handle the whole of the North American options price feed on a single box. That's the so-called Opera feed. You can read about that on the Intel low latency site. And here's a recent comment on Twitter, somebody just trying to test some performance there. So why would you use Rabbit in the end? It's because it actually does some quite complicated stuff for you that you might be tempted to write yourself, but we would generally advise you to think twice before you do that. It does deliver some pretty significant clustering and high availability properties. And it took us quite a long time to get these right, even using Erlang OTP, which already does that very well for the lower layer. It is a complete conformant and interoperable implementation of the AMQP specs. It does a lot of different functions. It's free to use, open source Mozilla license. We support it commercially, and there are lots of bundles for different platforms that you can just get unzipped and up and running very quickly. So it's there, give it a go, and let us know if you have problems. This is sort of to read later. These are various links, the website, the repositories. My company, Cohesive, has built virtual servers that are ready to run on Amazon Cloud or on VMware or Xen. I recommend you try those out. This is a list of links that I collect on Delicious that you might find interesting. There's an IRC channel and various other references. Some of the stuff from later today you should check out on the L-Shift blog as well. So that's it from me. It's an open source project, so we'd love people to get involved. What I'm now going to do is hand over to Matthias, who'll talk about the architecture and the engineering of it, and then Tony to talk about the new stuff. Okay, thank you.
I'll go into the details of the RabbitMQ architecture and the reasons for why we choose Erlang ATP. I just want to say a few words about Erlang itself, because otherwise the rest of the talk really isn't going to make all that much sense. How many of you guys here have actually written a few lines of Erlang code? Okay, I hope I wouldn't bore you too much for the next few minutes, but just be patient, bear with me. So, on this slide here, I've just put up a quick history of Erlang, and there's two main points I want you to take away from this. Firstly, that Erlang actually has quite a long history. It's been in development for 20-odd years, and significantly, that's all been in a commercial setting. So this is not some PhD student's pet project that they came up with last month, right? It was first conceived by Ericsson in the mid-80s when they were looking for new platforms and technologies, programming languages, to build their telecoms applications. And for the first few years of its life, it was only used in-house by Ericsson. That had some advantages in terms of language development, because you basically had the users of the language sitting right next to the developers. So there was quite rapid feedback that allowed them to refine the language and the platform. And it got open sourced in 1998. And over the last few years, just the last couple of years actually, there has been a real surge of interest in Erlang ODP, which you can probably ascribe to a number of factors. So firstly, the rise of multi-core systems. Multi-core systems have become really prevalent only just over the last few years. And Erlang, being a platform that was designed to handle concurrency and parallelism, is quite well suited for that. So that's one reason why people become more interested in Erlang ODP. And another reason is grid computing, which is a form of distributed computing, another area that Erlang has been designed to handle really well. And finally, internet scale computing, dealing with protocols, that kind of thing. Erlang coming out of the telecoms world, which is very, very protocol heavy, protocol standards heavy, in fact, has been designed to take care of that really well. And for those of you who don't know Erlang yet, there's a new book out, well, it's about a year old now, which is well worth a read. It's a great introduction to Erlang, lots of examples. It really gets you excited and to use the language. Right, so what's it all about? At the heart of Erlang, there are just very, very few concepts, really. An Erlang system is a collection of communicating processes. And process creation is extremely fast. You create processes with this little statement I've got up there, that spawn statement. What you get back is a process identifier, which you can then use to communicate with that process. Processes are extremely lightweight, which allows you to have tens of thousands, hundreds of thousands of them in a typical Erlang system. No problem at all. That's quite typical. Processes share absolutely nothing between each other. They have their own private memory. They have their own garbage collection, which gives Erlang some soft real-time properties. Inside the process, what's running is it's a functional code, functional programming code. Which of you are familiar with functional programming? Lots of you. Good. So I won't have to explain that. You get pretty good abstraction, concise code, etc. Significantly, though, you also don't have mutable variables, which just takes away one whole area of concurrent programming that becomes a headache. So how do processes exchange data then? Well, they communicate with each other by message passing. Message passing in Erlang is asynchronous on the sending side. So we have this process there on the left, addressing the process on the right by its process identifier or PID and sending it a message. That's the sending side, asynchronous. It sends, that proceeds. On the right-hand side, the process is sitting in a blocking receive with an optional timeout. When the message arrives, it starts processing, continuous processing. What happens when the thing on the right-hand side is doing something else, i.e. it's not sitting in a blocking receive when the message arrives? Well, in that case, the message gets enqueued. So every process in Erlang has a little message queue, or a large message queue, possibly. The messages get queued up when they arrive. On top of using those basic communication primitives, you can then quite easily build more complex communication patterns, such as RPC, multicast, etc. And indeed, the Erlang library contains libraries, APIs for doing exactly that. Last point here, that the same code you're seeing up there works just as well in a distributed Erlang system. So imagine F and G being on different nodes in a distributed system, same code, just works. so far I've only spoken about Erlang the language, but there's this free little acronym now, OTP, that always gets mentioned as well. OTP stands for the Open Telecom Platform, which is really, well, badly named. It has absolutely nothing to do with telecom, really. What it is, it's a collection of applications, libraries, and tools, all built on top of Erlang, so all using the Erlang core principles, and hence all working really nicely with each other, and designed to build highly reliable, scalable, distributed systems. And you also get a whole collection of system design principles, patterns of usage of how you should implement a system that is scalable and reliable. So that's OTP, a very important part of the whole package. So why did we choose Erlang OTP for RabbitMQ? Well, the first point is that when I looked at the AMQP spec about 2 years ago, something like that, I immediately thought that it was a pretty good architectural fit between what AMQP was trying to achieve and what Erlang OTP actually does. So remember this picture here, which Alexis briefly showed on his slides. So we have clients on the left, servers on the right, TCP IP connections, this notion of channels, which is multiplexing of logical data and command streams across a single TCP IP connections, queues and exchanges, etc. So that's the MPP architecture. Let's just focus on the server side only for the rest of this talk and drill down a little bit. So this is still just on the logical MPP architecture side of things. So we got something to deal with the whole TCP IP communication side of things. We got the multiplex and demultiplexing to get the subdivision of one TCP IP connection into multiple channels. This layer there is new on this slide. What it deals with is rather than sending all commands kind of atomically as undivisible entities across the network, you can actually subdivide them into something called frames. And the reason you do that is so that when you have large messages, say you have your 1 gigabyte message, so that you don't clog up the entire communication channel. By dividing the message into frames, these frames can then be interleaved with frames for commands on other channels, so other channels can continue to do work while you're sending this really, really large message. So that's what that layer is dealing with. And on the right-hand side, we got queues, exchanges, bindings between them, and channels. And that's the RabbitMQ server design. So, flicking back and forth, you can see there are some differences there, but broadly it's a pretty good fit. Each node on the slide here corresponds to two things. It corresponds to a module in our code base, an Erlang module in our code base, and it also corresponds to a process or collection of processes in the running RabbitMQ system. Now, this is pretty neat. Firstly, we get very concise code because of this nice architectural fit. Secondly, it makes it really easy to move between a logical design that you have for some feature to the implementation. So as the spec evolves, as we think of new ideas, as the community thinks of new ideas, new features to implement in RabbitMQ, they can immediately move from that logical design and pinpoint the area in the code where that feature does live or should live. Now, how small is the code really? Well, it is pretty tiny. The entire RabbitMQ server code base is just under 5,000 lines of handwritten Erlang code and another 1,100 odd lines of auto-generated code. The bulk of the auto-generated code is in the kind of MPP codec, the layer that deals with taking bytes octets off the wire and turning them into MPP data structures representing Erlang data structures representing MPP commands, and vice versa. That's all auto-generated, and in fact, most of the MQP implementation take a similar approach. They take the specification, an XML document, in fact, and generate a codec from it. The bulk of the handwritten code is, not surprisingly, in our queue implementations, after all called the Advanced Message Queuing Protocol, so that's where most of the code lives. And a lot of the logic of AMQP also lives in the channel end. Nisia is Erlang's distributed database, which we use to store routing information for exchanges, bindings, and queues. So this nice fit between logical architecture and our design is one reason why our code base is concise. Another reason, pretty important reason, is that Erlang has some quite neat features that help us keep the code as concise. And I just wanted to show a couple of them. Firstly, this is an example of some of the auto-generated code. Doesn't look very auto-generated, could be handwritten, but yeah. This is from the incoming side of the codec. So we take some octets off the wire, and we want to decode them into an Erlang data structure representing AMQP's basic publish method, which is the method with which you publish a message. And we are using something here from Erlang called binary pattern matching. So up there, this thing, it takes this sequence of octets and decomposes it. So for instance, we have 2 length prefix strings in there, 8 bits of length information followed by a string of that length. And there's syntax in Erlang to support that. And you can probably think of ways of making that even more concise, but it would probably become unreadable. So I think this is just about, the balance is just about right. And similarly, on the outgoing side, there's another feature called binary comprehensions, where you can write similar code to take an Erlang data structure and turn it into a byte stream. This comprehensions and higher order functions, nothing unique to Erlang at all. Anybody who's done functional programming will know about these. Here's just a little example that I pulled from our code base where we're using these. So this is an unordered parallel map. Takes a list of data items, applies a function to each of them in parallel, collects the results, doesn't care about the order in which the results arrive. And that's 5 lines of code. So another reason why we thought Erlang ATP would be a good choice for implementing RabbitMQ is that we get pretty good performance and, more importantly, scalability. Why is that? Well, Erlang gives you very fine-grained concurrency, very fine-grained parallelism, which allows us to exploit parallelism that's inherent in the AMQP model in kind of 3 different dimensions. So firstly, every message going from a producer to a consumer as it travels through the RabbitMQ broker actually goes through an 8-stage pipeline. There are 8 processes, 8 distinct Erlang processes involved, which you can kind of see on this picture here, kind of going around this loop. Yeah? Which of course means if you, even for just a single producer and consumer, in theory, if you have an 8-core machine, you can see an 8-fold speedup if you keep your pipelines busy and the stages in the pipelines are perfectly balanced, which of course they aren't. I mean, some of these processes do more work than others, so you won't get an 8-fold speedup, but you will get some. Another degree of parallelism we exploit is that between channels. So each channel in AMQP is completely independent from all the other channels. We have a few processes, these 3 here, instantiated for every single channel, so we get parallelism there. And then 1 level up, the same happens for connections. Next thing I want to talk about is management and tool support, of which you get quite a lot with the Erlang OTP platform. Erlang OTP was designed to keep telecom systems up and running, the proverbial 24/7, never go down systems. So there's an awful lot of tools that come with the platform that allow you to poke around in the system, figure out what's going on, tweak it, tracing, debugging, all that kind of stuff. So the main tool for looking at a running Erlang system is the Erlang shell. You can just have a running system, bring up a shell that connects to the system, and enter ordinary Erlang expressions to poke around and figure out what's going on. One back, that's it. So here's an example of using the Erlang shell to figure out what process is eating all memory. So say we have our Rabbit instance, and it's getting fatter and fatter, so we're probably feeding it too much. We want to figure out what process is responsible for that. So that's an ordinary Erlang expression here typed in the shell. We get hold of all the processes, figure out what their memory consumption is, sort the list, reverse the list, get the top process, and you can see it there. That's the process identifier there, by the way. Just that triple there, and its memory consumption is right there. That doesn't tell us an awful lot. We want to find out what kind of process is it. So we asked the process for a bit more information. That will probably all look rather cryptic to you, but to the trained eye, you can discern that there's an AMQP process here. It means it's one of our processes representing an AMQ queue, and it's actually for the queue called test queue. So armed with that information, we can then poke a bit more around the system to figure out why that queue is consuming more and more memory. Another example, this time something that didn't come out of the box with Erlang MPP, it was something we implemented ourselves. A little management application called RabbitMQ Here's an example of using that to set up a RabbitMQ cluster. 5 commands to take 2 separate RabbitMQ nodes, join them together in a cluster so they have one logical protocol. That's all it takes. Left the best bit to last. One of the main reasons why we choose to use Erlang ODP is because we can actually hide it. You don't need to know anything about Erlang in order to work with RabbitMQ. And why is that? Well, it should be pretty obvious. AMQP is a protocol. The beauty of protocol-based standards is that when you are a user of the protocol, a client, you don't care what your server is implemented in. There's a whole bunch of libraries for most programming languages that you can use to implement your clients, or you can even write clients yourself. It's not all that hard. The spec is published. You can auto-generate code from it. And so that gets you quite a long way in terms of just hiding OTP. For those who want to develop with RabbitMQ or want to administer a RabbitMQ system, we need a little bit more to make kind of the Erlang OTP transparent and hide it a bit. So we've packaged RabbitMQ, so you get Debian and RPM packages, you get nice little log files that get rotated, all the kind of stuff a sysadmin would expect. So just to sum up my part of the talk here, before I hand over to Tony, what it boils down to is that Erlang OTP has a sweet spot when it comes to dealing with protocols. Right. Shouldn't come surprising given its background in the telecoms industry. But if you're considering Erlang for some of your projects, if they have to do with protocol handling, then Erlang is a pretty good choice. Right, and with that, I'm going to hand over to Tony to talk about the future of messaging and our XMPP gateway.
I'm just going to talk a little bit about how messaging is in use on the web, sort of as I see it, and it's ubiquitous. I mean, you see messaging, queuing in many applications, many different environments, from email to the web to RSS and Atom feeds, instant messaging, of course. People even abuse file systems to get sort of poor man's messaging and queuing going on. Obviously, one of the other things that people will use is a SQL database if they don't have a messaging system in place. So everybody's doing it, but nobody's quite got it right or abstracted out the primitives of messaging yet. So that's what we've been trying to look at in the AMQP working group. We're trying to take AMQP as it stands, which is a client-server protocol where you have a server in a well-known location and clients that are anonymous connecting to it. And we're trying to grow it out so that it's a family of interacting protocols that can scale up to the whole internet, just like HTTP does. So looking at that and thinking about the sort of the essence of messaging, or the essence of these kinds of distributed system, we've come up with a few things that we think characterize messaging. Now, the first one is that when you look at internet scale applications, you see that people are trying, consciously or not, very hard to encapsulate state. They're trying to get state into small, well-known, well-named locations, and they're trying to keep the networking fabric from being stateful. They're trying to keep it as stateless as possible. So messaging being fundamentally stateless, applications fundamentally stateful, that's the sort of fundamental dichotomy, or the fundamental two components in the system. The second thing that we notice is that people use messaging to, in a lot of cases, arrange for the transfer of responsibility for a message. So if you look at the delivery of a message, I'm sending a message to you, I don't know whether you've got it, so what I need to hear back from you is an acknowledgement. Now, in a lot of systems, that acknowledgement is an acceptance of responsibility, so that now if you've acknowledged that message, that means that I can blame you if you lose it. So that is a kind of a contract. And so we're looking at ways of sort of surveying all of these different systems in use and trying to look at the different sort of contractual arrangements that they have with each other between the participants in the network. The other thing about having a contract and having some transfer of responsibility is that you can then plan for failure. It's going to happen anyway. You may as well get the planning done up front so that when the network falls apart, you're not going to go running crying. And the responsibility transfer layer is also where issues such as quality of service, whether messages are stored on disk or not, whether they're stored in core, how many replicated copies there are. That's where this comes in. If I get that acknowledgement from you, then that's your promise to me that you have enough copies. You're just going to cope. The third aspect that we see is that messaging is used to synchronize the state of these stateful applications, stateless messaging. So state is sort of moved in buckets from one place to the other by way of messaging. If you like, you can think of the messages in flight as sort of photons. They're the carriers of the electric force. They're not themselves electrically charged. So messages carry state, but they aren't themselves stateful. So if you look at a common sort of application, this is a one sort of generic Lego brick that gets used a hell of a lot in distributed systems as a shared queue. Now, this is a place where messages arrive, and then they're stored until some consumer is ready to accept them. So there are two obvious aspects to a queue. There's one which is to do with the messages when they're in flight, and that's the messages arriving and departing. That's the transfer aspect. There's one which is queue browsing, which is looking at the queue kind of from the side as a whole, and that's sort of an examination of the messages when they're at rest. And finally, you can use queues to do synchronization, and you can use synchronization to do queues. It's kind of a meta-level transition thing. You can build an infinite tower of these things. I'll get onto that in a minute. To begin with, obviously, you're transferring stuff into a queue from the ends. So above this line here, representing an interface, a programming interface, you've got messages flying in flight. Then they sit down for a while, and they're in a known location, in a known state, and it's at this point, when the acknowledgement goes back along this edge, that the queue is promising a certain level of quality, of service level. And then finally, they get delivered on to subscribers out the bottom. The second aspect of queues, of course, is you can look at it as, this picture that we have here. You can retrieve individual cells in the queue. You can update individual cells in some systems. And finally, you can remove entries from the queue. And that final one is an interesting operation because by deleting something, you can see that as taking responsibility for it. I've got my copy now. You don't need to keep yours. So transfer of responsibility happens in that if a sender needs to reliably deliver something to a receiver, it can send it. And it can send it so long as it's got a good name, a good identity predicate. It can send it over and over and over again until it finally does hear back that acknowledgement. So that acknowledgement constituting, of course, acceptance of responsibility from the receiver. A second pattern of responsibility transfer is that we want to be able to support is the delegation of responsibility. Now, SMTP lets you delegate responsibility in that, naively configured SMTP will relay messages. Now, this is a problem, spam, obviously, because we think it's because SMTP does the acceptance of responsibility at the transport level, not the application level. So what we need to do is lift that up so that the emission of this SMTP 250 reply saying, I've accepted that message, it's mine now, needs to be controlled by the application behind the SMTP interface. SMTP being, fairly simple message transport protocol, doesn't really think too hard before it decides to accept a message. So what we want to do is instead permit applications to receive a message without accepting responsibility, then delegate it onto perhaps some other application, which then in turn finally does accept responsibility, which will go all the way back cascading through to the original sender. And this is hugely complicated, I suppose, and I'm sort of running out of time, so I'll just really quickly sketch the essential features. If you have a queue and you want to have a copy of that queue somewhere else, so for instance, think about TCP. It's got a queue of bytes it wants to send, and on the receiving side, it's got a queue of bytes that it's received. Bytes arrive, or messages arrive from the sender. They're put in the queue. And then this from the side view is used to synchronize the two views of the data structure, this queue of waiting messages, or bytes in the case of TCP. They're delivered onto the ultimate consumer, which, because we're lifting responsibility transfer to the application level, they have to then individually accept. When they do accept them, the from the side browsing interface is used to delete the messages or the bytes in the waiting queue on the other side. And then the acknowledgement can be propagated out to the ultimate sender. So you can use synchronization to do efficient responsibility transfer, because of course there's no need to send each of these as a separate message. You can bundle them all up, collapse them down into a single message, as TCP does. You know, it has its sequence numbers, which are effectively collections of names. They represent a set of messages, a set of bytes. So we're starting to get a feel for where we want to go. We're starting to get a feel for the kinds of patterns that the ideal messaging protocol should support. And AMQP, as it stands, gets us partway there. Of course, it does let you subscribe. It does let you publish messages. It has a simple notion of local transaction for grouping and for control of quality of service with this responsibility transfer idea. It has sophisticated routing, so you can do pub sub or you can do direct delivery. And of course, it has these queues so that you can buffer messages when nobody's interested in receiving them right now. So the challenge is to cleanly integrate the remaining features, this sort of shopping list of things that we've identified by looking at the internet at large. We need this from the side view. We need to be able to look at a queue as a whole. That's not there yet. We need it to scale up, which means that we need global addressing, and we need the service to be able to federate with each other cleanly in the manner of XMPP. We need a good public key infrastructure, but then don't we all? We need peer-to-peer protocol support, unlike HTTP, more like XMPP, where each participant in the network is speaking the same language and is able to be a full participant, both a server and a client, without having to speak different dialects. And we need good management. We need to be able to gather statistics on the operation of our network. We need to be able to enforce resource limits so that my cell phone that's speaking this new AMQP protocol doesn't get overloaded by the spams that people are sending it. Now, this table is clearly pretty complicated. Now, this is really just, please do have a look at this table in the slides that we're going to publish after this, because I don't have time to go through it right now. The basic idea is that I've been looking at things that are both protocols, there are some applications in there, and there are even some programming techniques, and they all have aspects of messaging or queuing that I thought were interesting. So we see right up the top there, AMQP, of course, has a lot of these things already. TCP, interestingly, has this notion of responsibility transfer. I don't have time really to go through this. XMPP is one of the few that are federated. It's also one of the few that are peer-to-peer. Relaying is an interesting one. SMTP relays, that causes spam. We need our ideal protocol not to relay by default. That needs to be a conscious decision taken by each application individually. And finally, XMPP is the lone system that has a notion of presence. We want to integrate that into AMQP as well. That's extremely useful. I thought I'd just touch really quickly on data languages. You saw earlier in Matthias's part of the presentation the binary parsing capability of Erlang. AMQP's binary protocol is reasonably efficient, it's reasonably low latency, it's reasonably fast. It does a good job, but it's not ideal. There are a few things that it's missing. So I just thought I'd talk really quickly about the ideal data language. It should be typed. It should have abstract syntax separate from its concrete syntax, so that you can design concrete syntaxes for specific situations, domain-specific situations, such as, if you're needing to debug it, then, JSON or an XML representation of the abstract data is a good one. If you're needing to go really, really fast, you can choose a binary representation that optimizes just message delivery and escapes out to a more general representation for other kinds of commands that need to go across the same link. It should be extensible. It should have a canonical form so that you can sign it. And if it was a widely supported protocol that people are using already, then that's ideal. There's nothing really that fits the bill. ASN.1 actually comes pretty close. Terrifying. Protocol buffers is a close second. Now, protocol buffers shares a lot of similarities, as I'm sure you're aware, with ASN.1. There are a few things that's missing. It only has the one concrete syntax at the moment. Having a few more defined would be great. It doesn't have a metacircular representation, which would be just lovely, being able to express the protocol buffer types as protocol buffer messages. And it kind of wins hands down for ASN.1 in the area of sort of simplicity and the availability of tools. ASN.1 compilers can be found, but it's a little awkward. And just to sort of close off, we implemented an XMPP AMQP gateway, and that taught us an enormous amount about the kinds of things we might want in the perfect messaging protocol. It seems that they complement each other pretty well. XMPP's internet scale addressing and federation are fantastic, something that AMQP is lacking. Its presence model is really interesting, and for AMQP to have life cycle events over the exchanges, queues and bindings that it supports would be really useful. But on the other side, XMPP is lacking a sort of a mandated store and forward capability, a Lego brick of a shared queue. It doesn't have programmable routing and filtering. It doesn't have transactions or responsibility transfer yet. All of these things you could add to XMPP, they just haven't been done yet. PubSub has some of these aspects, but it's missing others. So that's it. I mean, I guess I've been talking very quickly about the kinds of things that we're looking at to try and take AMQP to the next level and try and take it out to internet scale. All of the things that you see here are being worked on in the working group as we speak, more or less. We're hoping to open up the community. Anybody who's interested in this kind of thing, please do get in touch with the AMQP working group. We'd love to hear from you. We're actively soliciting expert involvement. And RabbitMQ, very much the same. We really want people to give us feedback on what it is that we're doing. Obviously, we're looking to implement features to track the AMQP 1.0 release that will be coming out soon and to make it run faster. You can grab it. Please do download it from our website. It's available today. People are using it in production. Try it and let us know how you find it. Thanks very much.
So I thought we'd do something interesting in the questions where we'll sort of alternate with the Google Moderator webpage and people actually here. So to start with, one question for the webpage. Is Erlang better suited to text-based or binary protocols?
Right. I'd say it's almost certainly better suited to binary protocols because it has very sophisticated binary pattern matching capability. Its text pattern matching is done along the same lines. But with text, of course, you're suffering from variable length all over the place, and its regular expression support is improving. It's in the most recent release, it's got Perl-compatible regular expressions, but in previous releases, it had a more limited form of regular expression, sort of basic awk regex is not very strong. So binary protocols, it's very strong.
I think protocol buffers now has the circular however you express that,
right.
that you were after. If we can chat afterwards,
sure.
To check whether I understand what you meant.
Okay, right. So maybe protocol buffers does get to sort of
it's still early days in that.
Yeah, sure. Okay, the next one was how many lines of test code, and that's an awkward one to answer because given that it's a client-server system, we have an Erlang server. We also have clients written in a number of different programming languages, and we use these clients to exercise the server. So we've got some tens of test suites in Java with some...
Yeah, I think you'll probably find there's more test code in our Java client than there's code in the actual server. Partly I would like to say that's because we have lots and lots of tests, but it's more actually to do with the fact that we write the tests in Java. So.
Could you repeat my question to the microphone after?
Sure.
Yeah. So one of the selling points to this show that Ade put in was mentioning the word Twitter. Can you talk a little how this system may do to do a Twitter clone using RabbitMQ?
Sure. Well, we've been experimenting a little bit with this. I guess Alexis has some things to say as well. Oh, sorry. Twitter, right. That was one of the selling points was that we were to talk about Twitter. And so the question was, well, how are we going to talk about Twitter? If you think about what Twitter's doing, it's kind of like blogging in a way. It's kind of like micro-blogging, and so that's what the XMPP people have been talking about recently, is micro-blogging. And so with our XMPP AMQP gateway, we've been experimenting in that area as well. AMQP has support for a thing called a topic exchange, and micro-blogging is very similar to publishing messages into a topic exchange and having them routed out according to the interest expression of a queue representing an end user, a subscriber. Alexis, did you want to say something?
So we could talk about this quite a bit, actually, and maybe we could talk about it afterwards. But the first thing that Twitter does is it uses, as far as I understand, I could be wrong about this, but my understanding is that when you read from Twitter, you perform a select in the background. What's happening with Rabbit, if you use Rabbit to implement a Twitter-like implementation product or service, it's actually doing the select at the filtering stage. So every time a message arrives, the routing keys allow you to match on different utterances from different people with different patterns, and then route them to queues, whereas they're effectively cached, pre-cached for the kind of queries that you'd expect. We've experimented by creating something called Rabbiter, which you can actually use, download, see on GitHub, which is a fun prototype for seeing how easy or hard it would be to do Twitter-like behavior using RabbitMQ. We started from the belief that it would be possible to run the whole of Twitter on one RabbitMQ instance, and we think that's probably true, at least as far as message loads go, although it may not be true as far as HTTP-based read queries go. The Rabbiter implementation takes the XMPP gateway and which gives an XMPP interface to the AMQP server and allows you to declare statements like follow JID, JID being Jabber ID. So you log in with your Jabber ID because you're coming in through XMPP, normal plain vanilla instant messaging. You're not using PEP here. And so you can actually make Rabbiter your friend on Google Talk, for example. Just friend it. And then when you talk to the chat room that represents your chat with Rabbiter, you can make statements like follow Matthias or follow Tony, and it will then show you what they're saying to that chat room. So what's happening under the hood is that AMQP and RabbitMQ are performing all the filtering for you and queuing things up for you to read. And if you want them to be persistent, then you can make the messages persistent, etc., etc. What we'd like to do next, so that solves the fundamental, if you like, client-server version of a Twitter implementation with an XMPP front end, but it does not give you the ability to read things like old messages using a web page. So two things are happening at the moment. Number one, this is being added literally as we speak. I spoke to somebody in Seattle who's done a prototype version of this in the last 2 days, adding CouchDB as the inbox for old messages. So then the queues are essentially caching what CouchDB is storing on disk. And secondly, we've written up a design, which I would be very interested in your feedback on, for federating Rabbiter and actually decoupling the implementation from the AMQP-ness of the internal server so that people can implement a network of federated microblogging using a pattern that we've defined, but with any other kind of technology as well, particularly with PEP servers in mind. So PEP is the simplification of XCP60, XMPP pub sub, and its personal event protocol, and it gives you a kind of way of subscribing to remote utterances through XMPP. So an alternative way of doing microblogging is to use PEP. What we've done, and I'll give you a URL if you want afterwards, is define a pattern for federated microblogging that could either use Rabbiter in federated mode or a PEP server, or a combination of the two. That hasn't been implemented yet, but I think the design is relatively robust with respect to future implementation. So we seek feedback on that. Our goal then is to show that you can use networks of messaging systems to do federated microblogging. In other words, things like copying a blog comment from one blog somewhere, location A, to a set of subscribed interested parties in locations B, C, and D, possibly over multiple hops in between. And this allows, for the future, this would allow people to declare interest remotely in what's being said and get efficient updates and notifications about what people are saying about specific topics or in specific places or from specific sources. And the door was open to this kind of solution a few years ago when things like RSS and Atom became standard. But it's the belief of, I think, many in the community that you need more technology than those simple protocols define. And that's why there's quite a lot of interest in things like XMPP. Also, certain patterns for using HTTP. If you look at what Roy Fielding has written about this, it's quite interesting, commenting on the talk by Kellen and I can't remember the other guy's name, another one of the XMPP guys at OSCON, about XMPP versus HTTP. There's lots of different approaches to this microblogging problem, but it seems to be that it's quite interesting to a lot of people right now. Does that answer the question? Thank you.
I don't think there's anything else on there.
Well, I think in that case, that pretty much concludes this tech talk. We're all going to lunch.